Okay, so for those of you who are really not aware of fractional quantum Hall and 8 states and stuff, I think there are better teachers sitting here who will be filling you in from tomorrow onwards. So for the talk that I'm going to give, you just have to believe my words for that matter. Let's say that if we have fractional quantum Hall effect, there we have some extended states following, around the edge of the sample, which basically conducts the current, let's say, which is not completely true, which your teachers are going to correct you tomorrow. But for a naive experimentalist view, I can tell you that you can take that around the edge of the sample, we have some ballistic 1D channels, and these are the channels that I am interested in, okay? So let's say we have, also we have heard these words, topological state of matter, et cetera, and why particularly I will be interested in, quantization of heat flow, or why at all heat flow for that matter. So it turns out that we have, kind of digged in quantum Hall for last almost 40 years, and the main probe was mostly electrical conductivity, and we know a lot about this system. But then there are certain phase of matter, or let's say modes that run around this edge of this kind of systems. I think one name you guys all are aware of, in the backbench I'm meaning, Majorana mode, okay? This is something very fancy, and we are, many of us, kind of after it. So I was one of you. I also wanted to, do something in order to see if specifically some experiments can be done in order to identify this kind of topological, excited states, let's say, for that matter. Okay, so before I go into anything quantum, I just want to remind you guys about a simple definition of thermal or electrical conductivity. So I have a classical conductor. If I subject it to potential difference or temperature gradient, of course, current or heat will flow, and they look like this. Now the idea will be that I want to replace this classical conductor by a 1D ballistic channel. And that's where I'm heading towards, okay? But where I'm going to look for this 1D channel? So as I said, that there were these words that we have heard, topological state of matter. Again, I'm not going to describe this state of matter. You have better teachers here, they can talk about it. And this is one of the current review article that we have. So if I read it for you, these are disordered liquids, and basically they have entangled many body states, which people are interested. I think theoreticians are more interested than experimentals like us, because we cannot do much. It's like in theory you can do a lot, and for us we have to still work a lot harder. Never mind. So what we are going to, what is the platform that I'm going to use, let's say, if I want to dig in this kind of many body states? So this fractional quantum Hall effect was one of the first known topological state of matter. So this is some platform that we can actually use for us to study, where electrons are basically confined in 2D world, and they dress up like new entities, which, as Jendra said, composite fermion. I'm going to mention them again, just to repeat and make my case. And then these emergent quasi-particles, by the way, are known as anyons, and they are different than electrons, let's say, okay? So they don't specifically obey exchange statistics which are same as bosons or fermions. Any statistics give them the name of anyons. And in this fractional quantum Hall effect, basically, again, the theoreticians can give you a better picture. The bulk edge correspondence basically give us a good handle where we can actually access the localized quasi-particle which are in the bulk. And by just measuring the properties of the edge extended states, as I said, the conducting 1D ballistic modes, we can really learn about the bulk modes, the bulk quasi-particles. So what we experimentalists can do is we can measure charge current, current fluctuation, thermal currents, and interference, et cetera, in order to learn about these kind of systems. Okay, so now I'm going to say something about which all of you know. It's like exchange statistics in 3D, that we are aware of one kind of particle which are bosons. When they go around each other, they don't pick up anything, nothing changes in the wave function. Then there are fermions. When a particle go around the other one, basically, the particle exchange their places, they pick up a negative sign, a phase pi. But in both these cases, when a particle goes around another particle, basically nothing changes. But in case of 2D, the exchange statistics is restricted because of the fact that these particles are actually now restricted in 2 dimensions. They cannot go in the z direction for that matter, let's say. So in case of anyons, when the particles are exchanged, they just pick up a phase, let's say theta, which is arbitrary phase theta. And when a particle goes around another particle, it picks up a phase 2 theta. But what happens that if we can do this kind of exchanges one after another, they basically commute. So it doesn't matter which is done first, which is done second. Eventually, this statistics is called the abelian statistics. But as I mentioned before, there are certain particles like Majorana, or I can call excitations, that they have degenerate ground states. And when they go around, like when they are exchanged their position, 2 particles exchange their position, basically things are not as simple as the anyons, the abelian anyons I mentioned in the previous slide. But then here, instead of the simple multiplication, there are matrices. And because matrices often don't commute or something, we end up with non-abelian anyons. Okay, so far so good. So we can have variety of particles, and thanks to this quantum Hall system, which basically gives us all the spectrum of particles available under this same similar background that we will have for this 2D electron gas. Okay, so our main platform for this talk will be the fractional quantum Hall effect, and which is by this, which I mean is it's interacting 2D electrons in 2D. It's the independent electrons are well understood already by now. Even there are fractional charges that has been measured and stuff like that. The study of anionic quasi-particles also has been done, like fractional charge has been measured, there are neutral modes, and there are ideas of abelian and non-abelian particles, which we are after, by the way. Okay, so again, the detail of these kind of systems, you are going to learn more, but just count on me when I'm talking about all these things very naively as an experimentalist. So we have insulating bulk. So let's say there is no current effectively flowing, no dissipative current is flowing through the bulk, so it's insulating. And there is bulk edge correspondence, as I said. So edge modes basically impersonate the bulk order. So by just studying the edge transport, we can learn about the bulk of the system. Again, quantum Hall, so it's a 2D electron gas. We subject it to high magnetic field, and then there are these Landau levels. You keep changing the magnetic field, you can have multiple Landau levels, and then there are multiple edge modes which are running around the edge. And we know through Landau Buttigieg, etc., that all these 1D channels basically carries this conductance, which is E square over H, which you have learned also in your first lecture this morning. Okay, so these are these 1D channels that I'm interested in, and I'm going to study their heat conductance. That will be the talk about. Okay, so this Hall effect was actually, this quantum Hall effect was first discovered in 1980, and you can see here these Hall plateaus that we learned in the morning, and then there is minimas in the RX6. And right after 2 years, so there again, this basically tells you that the bulk is localized and there is a propagating edge mode. And then after 2 years, a fractional plateau was actually discovered, which tells us that there are fractional quasi-particles, and it was explained very well by Laughlin, which also partly we heard in the morning. And if you really carefully see now, you will see that there is filling factor half, there is a dip in the RX6. So if we look into it carefully, and then there are RX6 0 for well-developed plateaus here. For for filling factor half, there is no plateau here, by the way, but there is a minima here. And then after another few years, there was a plateau in 5-half, which is an even denominator plateau, which was a bit different than all the odd denominator plateau that so far Laughlin can explain. And then how do we understand it? Again, let's say this unexpected behavior. It's like, so initially it was just some change of slope, but with good sample we can see that there is a well-defined plateau there and there is a minima there, which means that the longitudinal resistance is perfectly 0. So what may happen in nu equals to half if we try to understand? Maybe we can just extrapolate it to 5-half. So initially you can see that at nu equals to half, maybe it's not 0, but there is a minima. And what Gefen said, that we can think about composite fermions, where basically 2 flux quanta are attached with 1 electron, and this is your new excitation for this system. So basically, instead of free electron, you can think the system is now with composite fermions. So technically, this is a Shubnikov-Dihas oscillation around nu equals to half, where the effective field at nu equals to half, if we think is 0, we can go to this picture. But for 5-half, Moore-Reed came with a theory which can be just a superconducting phase of these composite fermions. And why we are talking about 5-half can be a superconducting phase? Because we saw that 5-half state has 0 longitudinal resistances. That means it can be a metal, it can be a superconductor, it can be any other exotic phases. But just because the fact Rxx is 0, the longitudinal resistance is 0, we can think of it as a superconductor. So what Moore-Reed actually explained this state as, that this is just a BCS polarized composite fermion state. So basically it's a p-wave Cooper pair. If we trust Moore-Reed's theory, and if 5-half state is really something exotic, then eventually I'm not drawing here all the edge channels. Basically, nu equals to 2 will have 2 integer edge modes for sure, but alongside with that, we will have a E over 4 excitation running around the edge along with another Majorana mode. And this Majorana mode is something non-abelian in nature that we learn about. And 5-half state was one of the first to be predicted to host such Majorana mode along the edge of the sample, and also they are plugged in the vortices in the bulk. Okay. So let's say I made a case that if we go to fractional quantum Hall, we will have fractional charge, and we will have also things like Majorana modes. And fractionally charged quasi-particles have been already found way back, 20 years back. People have already seen them. But unusual fractional statistics that we talk about, this anionic statistics, so far experimentally have not been demonstrated. Okay? So most of the why it was difficult, let's say, or experimentally it was difficult, but let's say now most of the experimental probe that I mentioned are sensitive to charge. And non-abelian particles are often, like this Majorana, often these kind of particles are charge neutral. So if you have something charge neutral and your measurement schemes are often, sensitive to charge, it's really difficult measurement. Like the kind of measurements that we are aware of these days about Majorana fermion, we know that, it's like a S-wave superconductors are coupled to, spin orbit material, and then you have looking for zero bias peak. So it's an energy in zero, it's a zero energy peak that you're looking for, et cetera, et cetera. The thing is that it's a neutral, neutral mode that you are looking for, and your measurements are often, sensitive to charge. So that basically makes our life as experimentalists a bit difficult. And here comes the role of this heat current or thermal measurements. So the thermal transport actually may distinguish between the abelian and non-abelian. Why? Because it seems, by the way, what I'm going to tell you here now about the limits of quantum limit of heat flow, it's true for 1D channel, okay? So for 1D electron, 1D ballistic mode, this number, you can see this prefactor to T is really a pure constant. So long back, in 83, John Pendry showed that this number should be actually universal for bosons or fermions. And Ken and Fisher then showed that even for abelian anyons, let's say E over 3 charge, E over 5 charge, this should stay the same. And then finally, if we have non-abelian anion in the system, let's say Majorana, this is a name that we are all kind of aware of and pretty excited about doing something around it. This can actually take a half integer value. The prefactor to it will be n plus half. I'm calling this one kappa naught, so half. And let me mention here that the half comes because of the fact that Majorana is half of electron. Okay, so if it will be some other parafermion, it should be something different, which I think Jenand can tell us tomorrow. So this half particularly comes because of the fact that Majorana fermion is, excuse me, half of electron. Okay, so I made the case like why I should actually, study heat transport. I made the case why I should be looking it in the fractional quantum Hall state platform. Now let me go to what exactly I want to measure and how exactly I want to measure, because I'm an experimentalist, okay? So by the way, we are not the first group to measure heat, okay? There were people who were doing it before. So for phonons and photons, it has been done in 2000, early 2000. And then there were work for electrons have been done actually long back by Lawrence Molenkamp, and then there were some following work. And this is the work that we have followed. So our work is kind of a generalization of this work that has been appeared in Science in 2013 by a French group. This work was done in integer quantum Hall. We extended it further. Anyhow, so the working principle of my experiments is very simple. Because it's a two-probe measurement, I heat one side of a conductor. Let's say I have a hot reservoir, the temperature I can measure, I heat it by something, I will explain to you later. And let's say I heat it up to temperature Tm. And then I have a cold reservoir. I'm an experimentalist who work with the dilution fridge, so cooling it down is not a problem for me. And then let's say I cool down the other side of that conductor to T0. And now I connect these two reservoirs with a 1D electronic or quasi-particle channels. That means I have only a hot reservoir, I have a cold reservoir, and I have channels, multiple channel, one channel, two channel, whatever, quasi-particle channels, which takes the heat out. Now, I put some input power, and definitely I dissipate some power to heat this metal or reservoir. How I do it, I will explain it in the following slide. But let's say I'm in a I'm a solid state system, so I cannot really get rid of the fact that I have phonons in the system. So there will be some electron-phonon interaction. I will lose some heat through it also. So there will be two ways that I send the heat from here to here is like a part which will be actually going through this 1D channel that I have. And of course, I'm going to lose some with the electron-phonon interaction. So if I have a dissipated power, total dissipated power J total on this hot reservoir to make it hot, then the heat can flow through, as I said, this and electron-phonon. So the idea in the experiment will be somehow eliminate the J phonon part in order to identify what will be the prefactor. And that's what I do, actually. So these are electron and this is phonon. And here in this experiment, all we do is we measure temperature. We do nothing fancy. We just measure temperature. So the electron temperature of the ground contacts, T0, is what we measure. And also the electron temperature of the heated reservoir, Tm, is what we measure. And the power that we dissipate in order to make this reservoir hot up to Tm is what we know, because we know how much current we are passing in the system, okay? And then eventually we know what is the Tm and T0. And then if we can somehow eliminate this term by varying number of channels of what takes the heat out, we can just subtract it, and that's all. But if we are measuring in very small temperature, the phonon term is irrelevant because you can see it's square and it's 5. But if we go to high temperature, as I said, we can subtract. So that's how we deal with the data, and this is how we determine the K. This is a sample that we deal with. So these are like, we have drains where we measure the noise. And by the way, we measure noise in order to get the temperature. So it's thermal noise what I measure. So all I do is like I source some DC current. And this DC current basically enters this small metal island. And this metal island is the only way that these 4 different dark gray regions that you see, which actually are 4 different hall bars, are connected through this small metal island. And the current, the red current enters, and then this green current leaves this small metal island. So if we can do a small math, we know that there will be some voltage drop. There is some potential drop. And that basically gives us some power dissipation and heats this up to certain temperature. When I say certain temperature Tm, I mean that it's a, it's a steady state temperature. So I pass some current and I measure the steady state temperature after equilibration in this one of the drains. And hence, it's important that the size of this metal should not be too small, because if it's too small, electron enters and gets out. So it doesn't equilibrate with the temperature of this metal. It should not be too big, then I'm going to lose a lot of heat because of electron-phonon interaction. So it should be, about the right amount of size. We are not theoreticians, so we had to work on it, what will be the right size so that we don't lose too much in the phonon and we can still, look at everything nicely. Anyhow, let's say I wrote here nu equals to 2, n equals to 2, just to tell you that there are some gates. These gates, which I call QPCs, quantum point contacts, which allows me to manipulate how many number of edge channels I want to be out to the drain. Namely, I can really tune the number of edge modes, which is going to take the heat out of the hot reservoir. Because when I change the number of channels, the temperature is going to be different because heat is going out in different rate. And that's the key feature of the experiment, by the way. So then what happens, as I said, I measured Johnson-Nyquist noise. This is a typical data that you measure, and this is whatever fancy diagram of the sample that I showed you, it basically goes down to the fact that we have R Hall, because it's Hall resistances. So it's a combination of Hall resistances that only I have in the system. And I can measure in one of the drains, what's the thermal noise that I have. And what I do is I just inject DC current. So I inject DC current, I measure it 1 megahertz, what's the noise that is coming out. And this is how I guess the temperature of the hot reservoir, okay? And this I can do for multiple channels. Like I said, I have gates. I have 4 different mesas, so I have 4 different hall bars connected through the same point. So I have handle on, how many channels I will allow to take the heat out of this small metallic island. And by doing that, what I can do is this, that I can eventually subtract these 2 curves in the same temperature. And only the electron phonon depends on temperature. So if I subtract them, what I'm landing up with is what is the amount of heat this is carried by, the number of channels that I'm taking. So if I subtract this will give me, the subtracted graph will give me what will be the heat that is carried by 2 channels of whatever will be the particle in that I'm, taking the data. So we subtract. And by subtracting this, we can just get this prefactor. Okay, so now let's go to the real data. I'm not showing here the integer data as we repeated it first for ourselves to understand that yes, we follow the French work. And now, as I mentioned initially, that Ken and Fisher in '97 said that 1/3, namely therefore anyons, 1/3, 2/5, all this should not be different than what we will be seeing for, let's say, bosons and fermions. So in that case, if I really simplify the statement, if I have in 1/3 should be same as nu equals to 1, namely instead of 1 electron mode, in case of nu equals to 1/3, we will have 1 composite fermion mode. And eventually, it should actually carry a unit of heat. Okay, which I'm so far going to say kappa naught. I'm dropping the T because it's not needed for here, you to understand. And this is the experimental result that I have. So I had this, 2, 3, 4 curves of n equals to 2, n equals to 4, n equals to 3, whatever, and now I just subtracted both of them at, particular temperature. And this is the slope which tells you the prefactor of kappa naught. So basically it tells you that yes, indeed, for 1/3, every edge carries a unit of heat conductance, okay? A quantum of heat, basically. So far, so good. So Ken and Fisher was right about anions, let's say, but we wanted to go for more complex fractions. By more complex fractions in the lowest Landau level, yes? No? It's for everybody. It's n equals to 2 and 4. All I mean that number of edges. Those n's were actually number of edges. No, it's always there. So basically what happens that this electron phonon that I'm saying, because my sample was in 10 millikelvin, let's say, it's basically coming from the metal island that you have. That's our guess. But n equals to 2, 3, 4, whatever I'm saying, it's the number of edge modes. Okay. And I have the handle of having multiple edges because I have 4 different quantum Hall bars, right? So I have 4, so I can at least, even if n equals to 1, I will have n equals to 4, the maximum. And then I can go down to n equals to 2. Yeah. So this is what I'm trying to tell you, that for me, I eventually show you that I have, for individual edge mode, I'm having only 1 unit of thermal conductance, which tells you that you have 1 edge mode. That was what Ken and Fisher predicted, and that's what we measured. Yeah, that's what I wanted to show, actually. Yeah. Yeah. Yeah, so for 250 it will be 2. Yes, exactly. 250 should be 2, but we didn't measure 2 here. I want to go to further complex fractions for another reason, which I will show you. So you're right. So Ken and Fisher said that 1/3 should be 1, 2/5 should be 2, because it is 2 of 1/5 edges that we have, for that matter. Okay? Yes, sure.
Of the edge means
it's 1B. Like I told you,
you are considering 2-dimensional material.
It's a 2-dimensional material, but
yes,
the extended states that basically carries this quasi-particle currents, they are 1-dimensional. They are
yes,
only along the edge of the
It's
sample.
1-dimensional, means yes, you are considering like for a
I'm not
material.
being completely truthful, by the way. The teachers can tell you better, but yeah, effectively it's a 1D, let's say.
I'm confused whether you are considering 1-dimensional edge and how we define modes, like maximum is 4 and equals to 2.
The maximum is 4 because I have 4 such Hall bars connected together. Like I'm not saying in one Hall bar I have 4 such mode in 1/3. I have 4, you can actually connect 10 of them. It's like, I made the sample in a way that I can have up to 4 edges. Let's say if each Hall bar can have 1 edge, I have multiplied it by 4 by having 4 of them together. It's the device geometry. Let me go back for you. So you see, I have 2 edges in all of them. In that way, I have 8 edges together. So that's just it's an experimental trick that you use, because I cannot multiply. The moment I fix the new, the number of edges are fixed. I'm in filling factor 3, it's 3. But how can I multiply? I can have such Hall bar, as many as I guess, right? So here I choose to have 4, which means in filling factor 3, I can have maximum 12 edges that I can manipulate. That's what I'm trying, okay? Any other question? Yeah. Sorry, excuse me. I'm heating this one, yeah. Oh, I'm heating, but I'm not heating to 200 Kelvin. I'm heating between 10 millikelvin to 30 to 40 millikelvin. For that matter, it will be fine, okay? Okay, thank you. So as I was telling you, so this is what we wanted to say, that why we have eventually, actually what Ken and Fisher mentioned in this paper is this, that the heat conductance can give you eventually the number of edge modes which is effectively running at the edges. And that's where we actually concentrated in the more complex fractions. It's not because it's fancy to do more complex stuff. No, it's not fancy. It's because there was another reason for us. Why? Because the fractions which will be in between the half and 1 are 2/3, 3/5, 4/7. They are well known for many years. And they are well known also to basically host neutral modes. So there are neutral modes which are supposed to be bosonic, and they were proved to be present in these fractions. So it's like, I don't invent anything new, but there were some certain, things were known. But our interest particularly was into the neutral modes. Why? Because, as I told you, I gave you this introduction saying, oh, Majorana is neutral. Okay, so Majorana is neutral. There is already known some neutral modes there. So I should study first the bosonic neutral mode to see if they react differently than the bosons or fermions in the system, or they are actually already, something different, and I cannot really use this measurement scheme to identify, different kinds of neutral modes. So that was the original motivation for going to 2/3, 3/5, and 4/7, and let's see what Ken and Fisher said about it. So according to Ken and Fisher, for 2/3, we should have thermal conductance 0. Now, these numbers that I have showing you here, namely 0, -1, I will explain to you if -1, -2 kind of perplexes you. But these are actually thermodynamic limit. Namely, if your sample is very long and the heat flows, eventually what are they trying to say? It's like you add up, as many counter-propagating. So it's like, here why it's 0? Because it's like exactly equal and opposite edge modes are, one is taking heat from hot to cold and the other is coming from cold to hot. And it will be 0 only when everything mixes up, namely complete equilibration. And this complete equilibration needs a long length of the sample, right? While when 3/5, there is an imbalance now because there are 2 with 1. 4/7, it's 3 compared to 1. And these negative signs are basically, you may think, oh, so now the heat is flowing from cold to hot. No, nothing like this is happening. It's basically in the quantum Hall system, we have the edge modes, which is continuous. It's chiral and continuous. So whenever I'm showing you negative, it's basically, it's not the bottom edge, which is conducts the heat, but the top edge. Because if this is the edge picture for the bottom edge, let's say, the top edge will be completely opposite of that. So whatever is now taking heat out will be actually taking back heat in. Anyway, there will be 2 reasons for these 3 states for us is basically, as I said, like, it will be more of evidence that yes, Ken and Fisher was right, that, the thermal conductance can give us the total number of edge modes, which is running for all these complex filling factors. And then we will have also some idea about all this neutral mode, Like if I really going to claim to you next that, I can identify fancy edge modes, which are neutral, okay, so come with something which people know for edges. And so this is something that why 2/3 will be 0, like I told you guys that, it is equal and opposite, and given the fact that, there should be complete equilibration, which I already mentioned. And then this is the result of all these 3 states. The straight lines are going to be straight lines for me always because, my data, as I said, it's a very simple measurement that I do. So you see for 4/7 it's 2, for 3/5 it's almost close to 1. Don't expect from experimentalists like me more than, this. But for 2/3 we landed something with 1/3. 1/3 is something, it's a serious number. You are 2/3, you measure something 1/3. I must mention that when I plotted this, I was really not so smart about still this work. So I didn't realize that for 2/3, both the edges are equivalent. So the result I show you, actually it's for both the edges, because both the edges can carry heat, which I was naive at that time, so I couldn't. So I thought, oh, wow, it's 1/3. For 2/3, the heat conductance is, prefactor is 1/3, which is another nice number, you know. So maybe Ken and Fisher was not nice or not right, and maybe I didn't do something right. So I was not happy about it, and the only thing I could do in the same sample, because I cannot change the length of the sample, let's say for the equilibration that I said, but what I can do, I can change the temperature. So what I did, by saying I changed the temperature, I mean the temperature of the cold reservoir, namely the background electron temperature, okay? Now you can say, why Mitali you stop at 30? Well, I can of course go on heating it, but you guys saw that the phonon term is T to the power 5. There will be a certain temperature after this, the phonon term is going to be really, really dominant. So I showed you that this conductance quantum is basically 1 picowatt for Kelvin square. The thing is that it's a very small number. So I go to higher and higher temperature, which means that I'm going to subtract 2 graphs and extract a very small number. So the error will be really high. So that's the reason we stop at 30, because if it follows something, it will be. So the thing is that if 1/3 was a God-given number, like this quantization we know of, it should stay here. But no, it started falling. So we knew at that time that it's the equilibration issue. And as I said, I was really not smart at that time to understand that this is like both the edges. So basically you have to also subtract, divide it by 2 in order to know what is actually one edge is carrying, which is almost 0.15 or something, which is not technically 0, but in experiment getting a 0 is another story. But never mind. So we can explain this by a simple neutron cooling method, namely a hot edge is going and a cold edge is coming back. If there is a heat transfer, you can just do this math by yourself, maybe better than me. And then eventually this model gives us that yes, indeed, when the number of edges are unequal, up and down, then this quantization is reached quite faster. While you go to 2/3, you see you have to make the sample really long. And this kind of explains our result. So we proved here up to now to you that yes, indeed, for 1D electron mode, 1D fractional mode, and even for 1D neutral modes, these neutral modes are bosonic neutral modes, the quantized thermal conductance is indeed same. Namely, for bosons and fermions and anyons, so far there is no difference. Okay, so far so good. Now I think maybe you guys already forgot about the state 5/2, which was the only, at that time, like long back. After that, there were a couple of more other even denominator states have been found, but 5/2 has been always the star because people still wanted to understand it. So 5/2 is, is the only at that, let's say, one of the, special cases where you have even denominator. And Moore-Reed kind of gave a picture, which is a generalized picture of like as if you have composite fermion, and it's the, BCS state of composite fermion, namely the gap that we see in 5/2 can be a superconductor, P-wave superconductor. So let's see, before we did this heat measurement, what was already known for 5/2. So the charge is E/4, which was predicted by Moore-Reed and other theories, were already seen. There are upstream neutral modes. When I say this neutral mode, I mean these bosonic neutral modes that I already showed you for 2/3, 3/5 people have seen before, and it's spin polarized. So there are NMR experiments and others that show that this state is really spin polarized. But yet, if it is abelian or non-abelian, needs another information if we can see really Majorana mode, in this system. Like you guys know now, this superconductor with spin orbit, They see a peak, they want to see 2e²h, you keep doing it until you prove, yes, I see Majorana, without a doubt. So without a doubt, we'll need this half quantized kappa naught, which I said for Majorana to be true. So let's say, given all this, information that we had so far before our experiment, there were 9 such states which can be possible. And 4 of them you can, the Majorana I basically depict by this dashed arrow. So you can see in this side of the table, I don't really have this dashed arrow. That means it's not necessarily the 5-half has to be, explained using Majorana mode. Without Majorana mode also there can be explanations. And I think this 113 is a good explanation for 5-half state because it kind of have all the ingredients that I showed in the previous slide, UV charge, UV4 charge, neutral mode, etc., etc. And then there are these two states, this Pfaffian and anti-Pfaffian. Numerical works kind of showed that these can be the ground state of 5-half, which, by the way, is non-abelian. Okay? So the thing is that if I measure thermal Hall conductance and I land with a integer value, by the way, again, these numbers are again in long, like thermodynamic limit, long length of the sample is needed, that you equilibrate completely and then you get these numbers. So basically, if I measure something integer, I should be in this side of the table and I should say, yes, 5-half is not non-abelian state, it's completely, abelian state something. And if it lands here, then we will know, yes, 5-half is something which actually hosts Majorana modes. So this is my experimental result. Again, bunch of straight lines. And you can see that I have changed this electron temperature like, T0, the cold temperature. And as we go colder, we see that, this 2.5, which made us happy initially, that, oh, wow, it's, half good. It was increasing, which is not bad given the fact that from 2/3 we still know, right? There was some kind of non-equilibration as you go to lower and lower temperature. Well, I want to believe that because, that's my experiment. You can come up with something new for sure. I will be happy to discuss that. So let's say that knife picture is good and we are decreasing the temperature as we are making the electrons colder and colder. The equilibration, length is becoming longer and longer and we are landing with higher number, which is a good hand-waving understanding. And this is how that we go until 26, 25 millikelvin, the graph looks. And if you have a question that why I stopped at 25 millikelvin, well, for my experiments, which I definitely didn't go into the details, in order for me to have this quantization right and correct, I want the longitudinal resistance, the Rxx, to be 0. Okay, because I'm telling you, I measured the temperature by measuring Johnson-Nyquist thermometer. So I measure noise. So I cannot afford any other backscattering of current. I don't want anything to leak my information and take it to ground without reaching my proper detector. And that basically needs me to be on a plateau, which I think you guys are going to learn, who of you don't know, tomorrow. And the Rxx should be 0, namely no backscattering, okay? And this is how I landed with 2.5. Now, so far so good, 0.5 is not bad. For me, I was happy. Not really, but okay. The thing is, the state that we nailed in our experiment was actually, theoretically, was not the most possible case, okay? Because numerical people always often show, and they tried a lot, actually, They are not lazy people that they are just throwing on you something. It's not. So basically, they showed that this is not particle hole symmetric ground state, but rather Pfaffian or anti-Pfaffian. Actually, lately, anti-Pfaffian is the case, and that's the reason I said that I was not too happy to get 2.5, because I was also myself expecting it will be something around 1.5. Never mind, we think experimentally it's a good result. And because I said, I already said that PH-Pfaffian for sure or not, I cannot say, because we are still doing experiment, by the way. We are putting a lot of effort in order to identify. But then there are certain, theoreticians like our friends, they came up with, they supported us. They supported us that maybe we are not completely wrong. Maybe we are just, our understanding is weaker or something. So one of the theory I really is my favorite, it's Steve Simon. And he tells us that it's basically equilibration issue. You don't have proper equilibration. It's still anti-Pfaffian. And he can be right because of the fact that if we can actually, disentangle the charge spin separately. And this is the paper that Dima Feldman kind of tried to argue, because he is in the favor of PH-Pfaffian, but he kind of looking at to the point in problem in this different way to make us believe that maybe eventually PH-Pfaffian can be a good case. But the following talk, David is going to explain to you guys that how he looks at it, and for us as experimentalists, it's a good case. Like, we want to believe something that David says, so please follow his talk, because he gives the explanation that why my experiment may not be completely wrong. So, I don't want it to be wrong, and we are putting a lot of effort to make, pinpoint, but I'm like, I don't know how many experimentalists are here, but working in mesoscopic physics, accurately measuring a small number is not a small job, so we may need time. And eventually, theoreticians give us a lot of ideas in the meantime, so it's good. So I end my talk by saying that we believe that that our measurements do really say that there is some non-abelian character in 5-half, which is really good, because then we can really pursue this state in order to see, interference and stuff, to see, a non-abelian. Because again, people will not say, you don't think half is only a good proof for non-abelian. I still have to braid them. So there are still more ways to confirm it. But let's say this is a good step, because now I know, yes, I should look here for non-abelian if I want to, okay? And my talk cannot be completed without thanking the people that I worked with, the 2.5 years on this project. And this is my supervisor, Professor Heiblum, who actually were very much hands-on with me in my experiments. This is a PhD student who worked with me at least less than half a year, but he taught me a lot of stuff. Vladimir grows the devices, the samples, that gallium arsenide that I use, the material. And these are our theory friends, and also David, who kind of helped us to have confidence on our data and understanding. And with that, I thank you for your patience, and please feel free to ask me any question that you think I didn't really address in my talk. Thank you.